So welcome back to this third. Okay, so welcome back to this lecture on in singular perturbations and boundary layers. So today it is the third lecture, and we will focus on some special singular perturbation problems that come from some numerical methods for partial differential equations, namely fictitious domain methods with penalization. So let me first introduce what these methods deal about. So imagine you have a partial differential equation that is posed on a certain domain U, big U. So imagine you have a reaction diffusion equation on this domain minus Laplacian U plus U equal F. Let's say with directly boundary conditions on the boundary. And so fictitious domain method, the principle is to so instead of solving this problem on this domain big Q, which can be complex, the method consists in immersing this initial domain into a bigger but simpler domain. So let's say a square in this case. So and the bigger domain is a big omega. And so we replace the initial problem with another problem which is posed on the bigger domain. And the idea, so we need to modify the equation, of course, because now this is the fictitious domain. So we need to modify the equations, and the idea is modify the equations in such a way that we recover our initial solution, initial problem. And one way to do so is by introducing a penalization in the equation. So we are going to introduce a small parameter epsilon, and we are going to consider instead this problem, for instance, minus Laplacian U epsilon plus. Okay, let's say I'm not taking this here. I don't need it. Let's say you have just the Laplacian, and we are going to add a, chi over epsilon U epsilon. And we are going to take 1 minus chi f in big omega. And the chi is the characteristic function of the complementary domain. So I will call it small omega, where omega is big omega minus u bar. Okay? So this domain, we are going to call it the small omega, and chi is the characteristic function of this domain, and we are going to take the same also directly boundary conditions on the bigger domain, on the boundary. Okay, so this is one way to penalize the boundary conditions here of Dirichlet type, and just let's look formally why we are expecting to recover the initial problem. So here, just formally, if you take chi equal 0, chi equal to 0 means chi is the characteristic function of the complementary domain. So in U, here chi equal to 0, and here chi equal to 1. So when chi equal to 0, you have just minus Laplacian U epsilon equal F. So let's you are in the initial domain. So you have the same. You recover the same equation in the initial domain. And when chi equal to 1, you will have here 1 over epsilon and here 0. And just formally, because we are taking here a small parameter in the equation, when epsilon is smaller than 1. We expect to have this term that will be dominant in the equation, and so chi equal to 1 means we are in small omega. So this term will be dominant, 1 over epsilon u epsilon equal to 0. So this will imply u epsilon equal to 0 in the complementary domain. Okay, so this is just a formal analysis. In the limit, so this is really looking at what this gives when epsilon is equal to 0 at some point. So you see here that you recover the initial equation, and we will have u equal to 0 in all the complementary domain, and which means if everything works fine, that we will recover also u equal to 0 on the boundary of the initial problem. Okay, so this is just formally. So the equations we are considering here is, of course, the convergence of u epsilon to the convergence of u epsilon towards u inside the initial domain, inside the big U. And also we are also interested, like, for instance, in the order of convergence with respect to epsilon. Okay, so you can see here that this is a singular perturbation problem, because if you multiply everything by epsilon, then for epsilon different from 0, you have a second order operator. The degree of the operator is 2. But then when epsilon is equal to 0, you multiply everything by 0, you have a 0th order operator. So this is a singular perturbation. A special case of singular perturbation problem where we recover here a reaction diffusion equation, let's say. Okay, so just some literature on the subject. I didn't say here what is the, why do we do this? So I said that we can do this, for instance, if we have a complex geometry. And so we replace our initial domain by a simpler one. Okay, and the advantages of doing that, so for instance here, if we replace the domain by a square, we can use a Cartesian mesh to solve this problem. We can, okay, here we have the same boundary conditions, but if we have complex boundary conditions here, here we can take simpler boundary conditions on the bigger domain. And this is also can be interesting if the initial domain is evolving with time, and so this will avoid the need to remesh our domain at each time step. So there are, for instance, some numerical methods that are efficient for Cartesian meshes, such as multigrade methods, for instance. And so this is also one of the advantages of doing this, of replacing the initial problem by a penalized problem. So this problem we are going to talk about a penalized problem. Okay, so just some literature. Not for this equation, but for instance, Navier-Stokes equation. So when we consider that we have a fluid in a certain domain and that we have some obstacles, for instance, so the complementary domain can be the obstacle that we include in the computational domain. And just some literature. So for the Navier-Stokes equation, this problem was studied, for instance, by Angot, Bruno Fabry. In 1999. And what they used here is some weak convergence methods and these energy methods to show the convergence and also maybe the order of convergence. And then what we are going to see today is more using the boundary layer approach to show, to answer these two questions. So the reference for the boundary layer approach. So this is weak, using some weak convergence and methods, etc. And using boundary layers, this is, for instance, in Carbo, Paris, in 2003. This is using the boundary layer approach that we are going to use today. Okay. Okay, so as I said, you see here that we have a singular perturbation problem, and we want to answer these two questions here. And so we are going to do this analysis. In our case, I'm going to present the method in a 1D case. One-dimensional case. So we are going to take a model problem in one dimension, and so we are going to take the same equation, but in so we're going to take minus u double prime equal f with with the Dirichlet boundary conditions. This is on 0, 1. Yeah. And u0 equal u1 equal 0 on the boundary. Okay, so I didn't say here, we are going to start this first part by considering Dirichlet boundary conditions. And in the second part, we are going to consider Neumann or Robin boundary conditions as well. So this is our initial problem. And so what we do is that we are going to replace it by a penalized problem. And here, in order to just focus on one boundary, let's say that we want to impose the boundary condition at 0 using a penalization method. So okay, we are going just to focus on the boundary condition at 0. And so our fictitious domain, we are going just to add -1, to add this part. So this is our U, initial domain. U is 0, 1. And the complementary domain, we are going just to add it on the left part, will be -1, 1, for instance. -1, 0. This is small omega. And just to take the same, let's say, vocabulary for Navier-Stokes, we can consider that this is the fluid domain. And this is an obstacle, let's say, okay? Obstacle domain. So chi is the characteristic function of the complementary domain, which is the obstacle. So here we have chi equal 1, and here chi equal to 0. So we are going to replace the initial problem by a penalized problem. And so here the penalized problem is this one. So it's the same equation written here, but in one dimension. And just to simplify the calculations afterwards, I'll explain that afterwards, but we are going to take epsilon square instead of epsilon. I'm going to explain afterwards why. So we are going to take minus u epsilon double prime plus chi over epsilon square u epsilon equal 1 minus chi f. And the penalized problem will be posed on the old domain, which is big omega, which is -1, 1. This is big omega. This is our fictitious domain. And we are going to impose all boundary conditions, Dirichlet boundary conditions, at -1 and at 1. Okay, so this is what it gives in the one-dimensional case. Of course, first we need to show that this problem is will pose, but here you can either use Lax-Milgram theorem because we have coercivity, etc. Otherwise, what we can show is that we can split this problem into two problems. We can look at what happens in the fluid domain and the obstacle domain. And so the penalized problem is equivalent to two problems. Okay, so we are going to look at what happened on the fluid domain and obstacle domain, and so we are going to denote the restriction on the obstacle domain by W epsilon, and here, so the solution will be W epsilon on the obstacle domain and V epsilon. Okay, so this is just the restriction of the solution U epsilon, and the penalized problem is equivalent to, so on the obstacle domain chi is equal to 1. So this is the first equation that we have, minus W double prime plus 1 over epsilon square U epsilon equal 0. This is on the obstacle domain -1, 0, which is small omega. And on the fluid domain, chi is 0, and we have minus p epsilon equal f on 0, 1, which is the initial domain. Of course, we have W epsilon at -1, which is 0, and V epsilon at 1, which is 0. And then, so this problem is equivalent to this one with transmission conditions at the interface, which is 0. So we have continuity of U epsilon and of the derivative, because you can show that the solution here, we look at a solution at h1, 0, but then you will have also that the second derivative will be in L2, and so U epsilon will be H2, and so it's C1. The solution is C1. We have continuity. At the interface, we will have to satisfy W epsilon 0 equal V epsilon 0, and derivative is also continuous. And I will denote these by equations by some number, because we are going to use them afterwards. So we replace the equation by these 1, 2, and then these transmission conditions are 3 and 4. Okay. Okay, so this looks like, so this, if you look at this equation, you multiply everything by epsilon square, you see as what we saw in the first lectures, which was the case of a reaction diffusion equation, the singular perturbation problem related to a reaction diffusion equation, for instance. So here it will be a little bit more complicated, because we have some transmission conditions and another equation on another part of the domain. But we are going to use essentially the same procedure to so what we are going to do is construct an approximate solution. This is W of our penalized problem. So that is the methodology. We are going to construct an approximate solution and then look at the difference and show that some estimates on the error function. Okay, so let me just explain what I take here, epsilon square instead of epsilon. So what we are going to do here is that we are going to we need an ansatz of the solutions, which means we need to suppose a certain form for the solution. And to do so, we need some understanding of the equation. And okay, so we are going to suppose a certain form of the approximate solution and show that this form works. And so I didn't say that, but so here we are in a one-dimensional case. And in reality, we don't need to do all this analysis using boundary layers, because we can solve this explicitly. You solve this equation on the obstacle domain, this equation on the free domain, and then you choose the constants that appear there to satisfy the different boundary conditions. So you can solve this explicitly and then do some asymptotic analysis to see what happens. And so, or you can solve this by some software and look at what this gives. So just a small sketch of what the solution will be. Imagine at the limit, the solution will be the solution of the initial problem on the fluid domain with zero boundary conditions. So let's say the limit solution U0 V0 is this one. So you are solving minus, for instance, if we take f equal 1, you will have some parabola here. And then the limit solution inside the obstacle domain is 0. Okay? We expect to have u equal to 0 on the obstacle domain. So this is your limit solution. But at a given epsilon, which is small, very small, smaller than 1, you see here that the limit solution is not C1. Okay? While you know that u epsilon should be in H2, and in dimension 1, this is C1. So the solution of the penalized problem is C1, so you should have a continuity of the solution and of the derivative at this interface here. But you see that at the limit, you are not, in general, you are not C1. So here the boundary layer will not come from the fact that we are not able to satisfy the boundary conditions, but it will come from the fact that you have some discontinuity in the derivative at some interface. So imagine at some epsilon equals to 1, maybe I didn't plot it, but you will have something maybe that is like that, and here you will have something that should be C1. So you will have something like that, imagine. So what I plotted in red is normally C1. And if you plot this for different epsilon, what you are going to see is that, so the boundary layer, what we notice is that it will just be on the obstacle domain. It will be present in the obstacle domain. So all these are assumptions, of course, that we are going to show afterwards that it works, but it will simplify the calculation. I'm not going to suppose that I have boundary layer everywhere here. By doing some numerical simulations, or by computing exactly the solution, we notice that the boundary will be only on this part here. And also, this epsilon square, we are going to understand afterwards why I take epsilon square here, because in the asymptotic expansion, if I take epsilon, I need to produce some asymptotic expansion with the orders epsilon 1/2, for instance. Okay, that was not the case for the reaction diffusion equation we studied before. If you remember the lecture of yesterday, we had epsilon, and the asymptotic expansion was only powers of epsilon. But here we are going to see in the calculations afterwards that because the boundary layer, if you remember the boundary layer associated to our reaction diffusion equation, the thickness is square root of epsilon if we have epsilon here. So you have, let's say, exponential minus x over square root of epsilon, for instance, And when you derivate here, when you derivate once, you have 1 over square root of epsilon that comes, and this will introduce some powers of epsilon 1/2 in the asymptotic expansions in this case. Okay, so that's why we are going to take epsilon square in order to have an asymptotic expansion only with the powers of epsilon. Okay, let's take our ansatz. So as I said, we are expecting to have a boundary layer somewhere here, but only in the obstacle domain, in small omega. Which means that we are going to assume that the solution in the fluid domain has no boundary layer. There is no boundary in the fluid domain, which means we are going just to take the variable x. We are not going to need a stretched variable related to the boundary layer region. So we assume that v epsilon is v0 x plus epsilon v1 x. So it's a classical asymptotic expansion with respect in powers of epsilon, etc. While in the obstacle domain, we are going to assume we expect to have a boundary layer here. So we are going to have 2 variables. So I am changing a little bit of notations with respect to what we saw before, but it's okay. So this will depend on x, and then it will depend on the distance to 0 divided by the thickness of the boundary layer. And because we already know that for reaction diffusion equation, the thickness is square root of epsilon. If I take here epsilon square, the thickness will be epsilon. So normally I should take minus x, okay, minus x, because the distance here to 0 is negative. I mean, x is negative and the distance is minus x, but I did the calculation with x, so it will not change a lot of things. Let's stick with x over epsilon. I will detail afterwards how these terms are developing. So it's the same thing. We will have an expansion like that. W2 x over epsilon plus this, and so this is an assumption we do based on what we already saw. Okay, this is the thickness of the boundary layer. In the reaction diffusion case. And so I will develop here. So here we assume that we have a part that is only depends. So every w here, wi x, and this so epsilon is the thickness of this variable. We call it z. So there is a part. This is an outer part. Okay, there is an outer approximation that is outside of the boundary layer, and here we will call it w bar. And which depends only on x, okay? And then there is an approximation related to the boundary layer, which we will call w tilde I. And this will depend on z. Okay, here I will take x and z, but we will see afterwards that it will only depend on this variable z, as we did already for the reaction diffusion equation. Because what the aim of this part is only to correct this jump in the derivatives, which means that we are just going to need some values at the interface. And so I don't really need x, but I will keep it like that to prepare for the high dimensional case. So I didn't see it neither, but in one dimension, we don't really need all these calculations or this boundary layer approach, because we can do things explicitly. But the advantage is that of what I presented is that it is extendable to higher dimension, while the explicit calculations are not. Okay, so I am going to present the approach in general in also high dimension. But here, in reality, in this one dimension case, we can assume only this depending on z, because the boundary will be only 1 point, while in high dimension, we need this x, because the boundary, we are going to correct the value, for instance, at the boundary, and the boundary is not only 1 point. So we need to, in high dimension, we need to this variable x as well. And we do the same assumptions. We are going to assume that these correctors are only localized on the boundary and are smooth and localized on the boundary. And this is the assumption we did last time. Here, just I changed the notation. So we assume that derivatives with respect to z, to all derivatives of w tilde I go to 0 when we are far from the boundary. So here the boundary is the interface 0, and just because my variable z is x over epsilon, when we are far from the boundary in the obstacle domain, it means z tends to minus infinity. Okay, just we need to be careful here on the signs. Otherwise, I should have taken minus here. But when z tends to minus infinity, this goes to 0 for all. So this is with respect to z, so which means for all x in omega, if this is dependent on omega. Okay, so just here I changed the notation with respect to what we saw yesterday and in the 2 first lectures. So this is what we called theta before. Okay, the correctors, we called them theta. Here we are going to use these different notations, but it's the same thing. This is it was the uj, it's a uj plus theta j. Here we are going to use these notations, w bar and w tilde. Okay, so we have our ansatz. So what we do is the same thing as before. We are going to take this ansatz and introduce it, substitute this in the different equations, and to try to balance the orders of epsilon. Okay, before doing that, let's just so we are okay. So when we are going to replace w epsilon by this ansatz, we are going to need to derivate because we have 2 variables x and z. We are going to derivate with respect to x or with respect to z. So let's write once for all the chain rule, the formulas we are going to need. So let's say if you have a function w, in general, w that depends on x and z, we will denote differently the derivative with respect to x and the derivative with respect to z. So we are going to denote w prime derivative with respect to z, and w index z, the derivative with respect, this is with respect to x, and this will be the derivative with respect to the variable z. And so if you have a function, if small w x is, because it's what we have here, for instance, if I take this part, this is w x over epsilon. If you have this function, we are going to need to derive it twice, and so then we have these relations. Okay, we are going just to write what is the formula for the derivative with respect to x of small w. So you use the chain rule, so it's w prime Okay, plus if we derivate with respect to z, there will be one derivative of z with respect to x, which is 1 over epsilon wz at x over epsilon. Okay, we have this formula. So just the derivative of composition, and if we do it twice, then you will have here w double prime x over epsilon plus again 1 over epsilon w prime z, which is the same as okay, x over epsilon. And for the second part, we will have 1 over epsilon w z prime x over epsilon plus 1 over epsilon square w z x over epsilon. And here we have the same thing, so we can it's equal to 2 over epsilon wz prime x over epsilon plus 1 over epsilon square w z x over epsilon. Okay, so we have the formulas here, and now we are going to substitute the ansatz into the different equation and look at the orders with respect to epsilon. Yeah, so we start by different equations. We are going to start with equation 1. And so this part, the first part, is determining the different profiles. The objective here is to find the equations on the different terms here, okay? So we assume this decomposition, but for the moment v0, v1, etc. are unknown, so the objective is to find an equation on these terms. So this is the first part, is determination of the profiles. Okay, so let's start with equation 1. And let's try to write directly the inequalities, different orders in epsilon. So order epsilon to. So you see here in the equation, okay, we can multiply everything by epsilon square. We are going to stick with this form. So we have here 1 over epsilon square. So there will be, the least order will be epsilon minus 2. Okay, so there will be epsilon minus 2. So we are going to look, if we derivate w epsilon twice, are there like epsilon minus 2 terms? Knowing that when you derivate here, you are going to use the formulas I wrote here, which means that yeah, so you have some epsilon 2 to the power minus 2. Okay, so when we derivate w0, you will have this term, w0 zz over times 1 over epsilon square. With a minus here, you will have minus w0 wzz0. Okay. I think this is the the only 1 over epsilon squared that will come from, I think. And then here, so it will be plus W epsilon times 1 over epsilon squared. So we should look at the 0th order of W epsilon, which is W0. Okay? So it will be this plus W0 equal to 0. Equal to 0 because on the right-hand side we have 0. So this is what we get at order epsilon minus 2. Just a remark. Okay, I will not write here x over epsilon, but so everything is taken at when we are talking about W0 is taken at x over epsilon. Okay, but we are going to assume that we can decouple like these two variables. So this will be at xz, and we are going to so for the moment this is a formal analysis. Nothing is rigorous yet. The objective here is just to construct this approximate solution, so to construct these different profiles. And this is not necessarily unique. Well, so the idea is just to construct these. And in the second part, we are going to show that this is indeed a good approximation. Okay, so we are going to simplify here because W0, as I said, it's decomposed into an outer part and an inner part inside the boundary layer. So we know that W0 is W0 bar plus, okay, it's right, xd. So W0 bar, which depends only on x, plus W tilde xz. And so if we decompose this, you will have minus W 0 bar zz plus W0 tilde or zz, I don't know, plus minus, sorry. This should be 0. And we remember the assumption that we did on the boundary layer terms. They are vanishing when z goes to infinity. So here what we do is that if we take z to minus infinity, then this is all the derivative with respect to z go to infinity. So this will be go to 0. Okay, this vanish. And you end up with an equation on. And we also know that W0 bar depends only on x, so derivative with respect to z will also disappear. So you end up with W0 bar is 0, so which is normal because we are expecting to have, this is the 0th order approximation when epsilon goes to 0, and we are expecting to have a limit solution equal to 0 in the obstacle domain. So this is natural to find that. And when we find this, what we do is, because we want an equation on W tilde, then we take we make the difference between these two equations to recover what we neglected when z go to minus infinity. So then by difference, we get an equation on W tilde 0, which is this one. Okay. Okay, for the moment I'm going to just write the equations, and in the second part we are going to solve these equations. Okay, so for the moment we're going to stop here for this order epsilon minus 2, and we need to do the same thing at different orders. So just to be clear here, this is, I'm gonna write where this would be satisfied. So this is in small omega, And this is because it depends on x and z, which should be satisfied in omega time, and z is something is negative. Okay, if we are in the obstacle domain, x over epsilon is negative, so let's say r minus. Okay, so this is order epsilon minus 2. We need to look at the other orders. Okay, and again, it's the same thing. You should look here at what are the terms that will give terms of order 1 over epsilon. So when we derivate twice, okay, so for instance, you have here 1 over epsilon squared, and if it's multiplied by an epsilon, which means if it's multiplied by epsilon, this term here, we will end up with 1 over epsilon. So we will have minus W1 z. Okay, we will have this term. Okay, this comes from derivating this. Okay, if you derivate this, you will have epsilon divided by epsilon squared, this derivative. So we have this term, for instance, but we also have, if we derivate 1 over epsilon coming from here, if we derivate the 0th term, W0, for instance. So we will have plus 2 or minus 2W0 prime. There is a prime here. Oh, this is prime. Okay, and then this is this term here. To have 1 over epsilon, this will come from multiplying by epsilon W1. So you will have plus W1 equal to 0. Okay, so we get this equation. So you see it's a little bit calculatory. You need to be focused and to not make mistakes, because then it will affect everything afterwards. So that's why I'm checking at each time if I'm doing the good calculations. Okay, so we have this, and then it's the same thing. We write the this decomposition. Okay, so W1, there is a part which is W1 bar and W1 tilde. Okay, so if I decompose everything, it's minus W1 bar Z minus W1 tilde Z minus 2 W bar Z minus 2 W tilde plus W bar 1 plus W tilde 1 equals 0. And yeah, then there are simplifications. So the W bar depends only on x. So this is 0. The bars are not depending on z. Okay, this one will stay here. Again, you take the limit when z goes to infinity, minus infinity, to get rid of the W tildes, which means like you look at what happens like far from this interface. it's what we did last time. When we are looking at what happens at here, we can neglect the correctors. I mean, it's not exactly what I'm saying, but if we are here, we can neglect these correctors. So if we are far from boundary, there is no correction to be done. And so when z go to minus infinity, all the w tildes and their derivatives go to 0. Okay. So this gives that. I think, yeah. So we end up with w1 bar equal 0 as well. In this case, in small omega. And by difference, okay, because we want to recover an equation w tilde. Well, maybe this we are going to need to solve afterwards. And by difference, we get an equation on w tilde. So, okay, this was gone for life. The equation w tilde is minus w tilde 1 z plus w tilde 1 equals 0 in omega times r minus. Something like that. I think I forgot something, right? Sorry, this was also this term. I forgot it. This was 0. It was a tilde. So in general, it will not be 0. We will see, but it will be 0 here, but because it will not depend on x. But in general, we can have this term as well. Minus 2w tilde z prime equal 0. Okay, so you understood the procedure. I will give the other orders directly. It's the same thing, following the same approach. We get the other orders. So we're going to write. Okay, it's okay. So order epsilon 0. So we get these equations minus w2. Just a remark. So if as I said in this case, because we are in 1D, actually the tildes, the correctors will only depend on the boundary layer variable, as we saw for the examples we considered before. But here so if you work with just z here, the calculation will be easier. But this prepares for the high dimensional case where we need also this variable. Okay, so that's why we have more complex calculations. But okay, so this is the equation at order epsilon to the power 0. They're doing the same thing, looking at what happens far from the interface, and doing the difference. We end up with these equations on w 0. We obtain other equations, reality. And then we obtain by difference in omega times r minus and finally order epsilon So we obtain these two equations, minus W1 plus W3 bar equals 0 in omega, and minus WT dot VZZ plus okay. Okay, so we finished with okay, maybe we will not need this afterwards. Anyway, so we finished with the first equation, equation 1. We are going to see that the other one will be simpler because there is no boundary layer inside. So we look now at equation 2. And equation 2, if you substitute this ansatz inside, you are going just, and looking at the powers of epsilon, you are going just to find that minus V0 double prime is F. This in big U, which is 0, 1 in the fluid domain. Okay, so here we don't have a boundary layer variable. Then you will find that minus V1 double prime is 0 at the order epsilon, and then you will get minus V2 double prime equal to 0. Okay, okay. So you take this into this equation, you balance the orders. What you find is exactly this at the 3 orders, and then we are going to do the same things also in the boundary conditions. Okay, these the boundary conditions at minus 1 and 1 are simply the Dirichlet. We are going to write this equality in terms of orders of epsilon. So equation 3. We look at point 0, and then okay. So we will have just V0 at 0 is W0, 0, 0. Which means that we will have continuity. This continuity will in reality stay at the limit, so we will not have corrections there, let's say. Anyway, and then so V0 is the W0, V1 is the W0, W1, 0, 0, and V2 as well. And we can just write it V0, Vi equal Wi at x equal 0, z equal 0. Okay. And finally, we have the fourth equation. And I will need to erase somewhere. Okay, let's do it here, equation 4. So equation 4 is the continuity of the derivative at the interface. And here we will have something that will happen, because when we derivate with respect to, when we derivate w epsilon, we use this formula here, so we will have some corrections there. Okay, first thing, so v0 prime at 0. Okay, first we have here 1 over epsilon when we derive. So I will have some to look at order epsilon minus 1 first. So order epsilon minus 1 comes from w z0 at 0, 0 should be is equal to 0, because there is no, when we derivate the epsilon, there is no order epsilon minus 1. Okay, so this will be 0. And then order epsilon 0, so order 1. Yeah, order 1 we have here wz1, okay, which comes, what's, okay, if you take wz1, you will have epsilon divided by epsilon, and here you have w prime plus w prime, w0 prime at 0. This should be equal to v prime 0. I forgot, no, it's v1 prime at 0, or the v0 prime at 0. And order epsilon here, here it will be wz2 0, 0 plus w1 prime 0, 0 equal to v1 prime at 0. Okay, so we finished with the different equations. We have different equations on the different terms. So let me just, because what is important here is the equations we obtained. So I'm going to write them somewhere. Let's write the different equations here. Or here. So the second step will be to solve these equations, because for the moment we have equations, we need to take the equations with the boundary conditions and just try to solve them. Okay, so let's just, I'm going to put the equations we obtained. Okay, I will not say in W, etc. We know, because big W is defined in small, in the obstacle domain, and when we speak about V, it's in the fluid domain, etc. So we have this equation, and then we have this one. Okay, maybe I will just I will erase everything except the equations we need. Hopefully this will be sufficient. Okay, for the moment we need everything, but it's okay. Okay, so this second step is for the formal resolution of the different profile equations. So okay, so we will need to do that in a certain order. Okay, so let's start with the formal resolution. So first we have W0 bar is 0. Okay, so this is normal. This is the limit solution in the obstacle domain. This is fixed. Now it's fixed, and then we have this equation on Z. This equation is should be satisfied in W times R minus. So we can solve this. It's a second differential. So if you assume X fixed, then we solve in Z. This is a second differential equation. This is the equation we got actually for the reaction diffusion equation when we were looking for the correctors. It was minus theta square double prime plus theta equal to 0. And so we solve this equation, and you get W0 tilde. So normally it depends on X and Z. We are fixing X, and we are looking at the equation as a function just with respect to Z. So this is you have two solutions, minus 1, or so it's a sum of two exponentials, let's say, exponential minus Z or exponential plus Z. But then we remember that this should be 0 when Z goes to minus infinity. This is just because of the notations I took. Last time it was Z going to infinity. But so we should keep here the exponential with the plus Z if we want it to go to 0 when Z go to infinity. So this is some constant. I call it W small 0. I don't know if it's a good notation, but no, it's not a good notation. Okay, we have a constant where it's a constant with respect to Z, so it can depend on X. We are going to see that it will not. Well, we can choose it not dependent on X. And exponential Z, because we want W to go to 0 when Z goes to minus infinity. And so we keep this exponential here. And now we want to specify this constant, okay? So in general, we are going to use boundary conditions. Here, because this localized at 0, we are going to use the interface conditions at 0. So what do we know about? Yeah, you have it here, okay? So we have, that's why we also treated the transmission conditions. So from this equation, this is W0, and there is a part W bar which does not depend on X, so this will give you just W tilde. And we have that W tilde Z at 0, 0 is equal to 0. Is it this? Or, yes. So normally this you have this condition only at 0, but because so here we have a choice to choose we have freedom, let's say, to to construct the approximate solution. So this condition, we are going to impose it, and we are going to see afterwards that this will work. So if this condition, we are going to extend it to every x. So we extend this condition in all omega. Okay. We are trying things here, and then if it works good, then otherwise. So if we extend this condition in all omega, so we are going to assume that this is 0 for all x. And then so I take this expression, I derive with respect to z. This will give me ax exponential z. And this is, if we derive w0 theta. And at z equal to 0, this is ax. And with this condition, it will give you ax equal to 0. So in this case, we find that this is 0. So w theta 0 is also 0. Okay, we can take it 0, and this is also normal because remember, this is the limit solution. There is a limit solution outer approximation w0 bar, which is 0 because this is the limit solution in the obstacle domain. And as I showed you before, we don't expect to have, we will have continuity at the limit. So the solution will be something like that. So we have continuity at the limit. There is nothing to correct. I mean, we don't have a condition, something to correct here. We will have continuity at the limit. So that's why we have no correction to make at the 0th order. So, so what we find is that w0 is 0. Okay? So this will be 0. And then, so we are going to continue to solve the other equations. So we solve w0 and okay, I will get to w1 afterwards, but let's look at v. We should do it in this order. So w is 0 in omega times r minus. And now let's look at the v0. Let's solve v0. So the equation we obtained on v0 was this. Okay? But we will need boundary conditions. So we have minus v0 double prime equal f in the fluid domain. And then we need boundary conditions. Okay, so we are going to look at the boundary conditions. So big U was 0, 1. Oh, okay, I didn't write the orders, the equations on the boundaries, but if we look here, so v epsilon at 1 is 0. If we introduce the ansatz in this boundary conditions, we will get v0. Sorry, yeah, if you inject this here, you will get v0 1 equal to 0. Okay, so you have this boundary conditions at 1, and then we need the boundary condition on 0. So this is minus 1, 0, 1. This is the fluid domain. This is the obstacle domain. We need a boundary conditions on v0, so we're going to look at the other equations that we obtained, which give us some boundary. Yeah, you look here. Remember, you remember we had that v0 at point 0 is equal to w0 at 0, 0. w0 we already obtained it. It's 0. So, which means that v0, 0 is also 0. Okay. And yeah, what does it mean? So again, that we found that W0 is 0. This is normal. This was the limit solution here, and there is nothing. There is no correction to do. Let's say apparently at this level. And V0, we expect what we want here is to recover the initial problem. Remember, our initial problem was solving minus. So I erased it. So the initial problem was minus U double prime equal F in 0, 1 with Dirichlet boundary conditions. Okay. And what we get here, so V0 is exactly the solution in the initial of the initial problem. So V0 is U solution of the initial problem. Okay, so this is good for a moment because this is what we expect. We want to show that V epsilon converges to the solution of the initial problem in the fluid domain, and this was U, and this is what we find in this formal analysis. And then we need the other terms, so V1. Again, we need the V1, W1 in general, so we are going to see that we need to do it in this order because there is dependence between W0 and V0, etc. Dependence between all these profiles. So now let's go to W bar, to W1. Okay, so W1 bar is 0 from this equation. So I can erase it, and then W1 tilde. Sorry, this was W tilde. And then we have this equation on W1 tilde. And remember, we already solved W0, it's 0. So here this simplifies, we don't have this term here. And so this is W bar, and the equation on W tilde is something similar to W0. We have this equal to 0. And again, we solve this by looking at, by fixing x and looking at what happens with respect to z, and we get the same, same formula, W1 tilde x z should be some constant bx. So, I mean, constant with respect to z, exponential z, or z. And we need boundary conditions to specify the constant. So, and this we get from here, okay? Remember, W1 z0 z 0, W0 is 0, okay? And so we have this condition, and W1 z bar is 0. So what we have is W tilde 1 z at 0, 0 should be equal to V0 prime 0. So you see that why the order is important, because if I need the V0 here, so I should have obtained it before doing this calculation here. Again, this is a condition at 0, 0, but there is no harm to extend it because we want to obtain this constant. So let's extend this condition at all x. Yeah. And let's do this. So you have this expression. When we derive with respect to z, we get the same thing. And at z equal to 0, you will find that bx should be this constant. So what we get is that, so this is W1 bar. We find that V0 is the solution to the initial problem. And then here what we find that is that W1 xc is V0 prime at 0 times exponential z. And now let's go to V1. So V1, the equation is minus V1 double prime equals 0. In U, from the boundary conditions at 1, we know that V1 at 1 is 0. And we need the condition at 0, which will come from here, okay? V1 at 0 is W1, 0, 0. And because we already obtained W1, okay, we already have W1. So W1 bar is the 0. And W tilde 0, 0 is this. So we take this, okay? We just replace V1, 0 by its expression. And it's W1, 0, 0. W1 bar is 0 and so this is W1 tilde at 0, 0, which gives V0 prime at 0. Okay, this is V1. Then we need W2. From here, we have W2 bar is W0 bar, and W0 bar was already calculated. It's 0. I think there was some error here, but this was a derivation, but anyway, this is 0, and so we get W2 bar is 0. And we need W2 tilde. So again, we look at here to have the equation on W2 tilde. So W0 was 0. This will disappear. But W1 and also this one will disappear because so as I said, W1 tilde depends only on Z. So it doesn't depend on X. So when we derivate, this is derivative with respect to X. So we get this same equation as for W tilde 1 and W tilde 0. So we get that minus W tilde plus W tilde 2 equal 0. So it's the same thing. We are going to solve it. It's some constant Cx exponential z, and the boundary condition is given from this. W1 bar is 0, and W1 tilde does not depend on X, so this is 0. And we have this this condition, and if we do the same thing, like if we extend the condition in all small omega, what we get for the constant is V1 prime at 0. So we are going to, so we are not going to need the last equation. We have W0, W1, W2. What is remaining is just V2, but for V2 it's easy. We get this, and we get what I'm going to write here. So the same equation with V2 at 0, at 1 equal to 0, and V2 at 0 is given by W2, 0, 0, and W2 bar is 0, W2 tilde is this. So it's P1 prime at 0. Okay, so we're done with the profile, the resolution of the profiles. Oh, it takes a lot of time. Okay, so I suggest that we stop, we take a break here and continue afterwards the other part. Okay, so let's continue. So now that we obtained the different profiles of the equations of the asymptotic expansion, the objective now is to obtain an estimate on the error function. Okay, so let's introduce. So now the question is the convergence of the asymptotic expansion. Okay, and again, like what we did already last time, so here, in order to obtain the different profile terms, it's simpler to work with these expressions. But then, for technical reasons, in order really to recover these boundary conditions also on the error function, what we are going to do is we are going to localize the correctors. Okay, these are approximate correctors, and we are going to localize them. So what we do is just add in some cutoff function. Just change. It's what we denoted by sigma last time. Here we are going to change a little bit the notations. I will call this cutoff function theta. Okay, sorry for that. Theta was corrector before. Now it's the cutoff function. Okay, but it's okay. So let's introduce this cutoff function. So theta is the smooth function on, because the boundary layer we have it only on the obstacle domain. So, and the boundary layer is localized at the interface 0. So we are going to take theta such that, which is smooth in small omega bar. And which, same thing as before, we are going to localize it near 0. So theta will be equal to 1 in a boundary of 0. Let's say on -1, 4, 0. On the neighborhood of 0, of x equals to 0. And we assume that the support of theta is let's say -1/2, and it's not a good thing. Anyway, it's the same thing as before. We take some localization here. It's 1 near the boundary, 0, and then support it's -1, 1, 2, -1/2, for instance. I'm sorry, the support is -1/2, 0. you understand. And so we obtained that, remember, we obtained that W0 is 0, W1 also, no, W1 bar was 0, and so this theta, we are going just to use it to localize the correctors, okay? So we are going to put it in front of the W tildes. Okay, let's write the formula now. So we are going to look for a solution U epsilon, so of the penalized problem in the form in the following form. So we are going to look to, so V epsilon is the same formula, so it's V0 x plus epsilon V1 plus epsilon 2 V2x. So because now we want to do rigorous calculation, so this was an asymptotic expansion. Here I'm going to look at the error that we make, which means I'm going to look at the difference between V epsilon and all this. And this I can call some error function. You remember we called it W last time. Here I'm going to call it V epsilon R for remainder. And I'm going even to take epsilon V epsilon, because I'm going to explain afterwards. So we look at a solution in this form, which means that just we are looking at the error divided by epsilon. This is the remainder, and this is in the fluid domain. And in the obstacle domain, I'm going to take into account the fact that this is 0. So we know that this is 0. So then we will have epsilon W1 bar, which is 0. So we will not have this term. And then we will have epsilon theta x W1 tilde plus epsilon square W2 bar also was 0. So we will have only theta again, W tilde 2 x over epsilon plus a remainder that I will take in the form epsilon W epsilon R x. And this is in the obstacle domain. Okay, so to simplify the notations, let's maybe this formula I will need. Okay, now okay, I will just rewrite. Okay, I don't need W0, W1. We only need, so V0, we know that it's solution of the initial problem, and W1 tilde, maybe I will need it. So just here, W1 tilde is V0 prime 0 exponential Z. Okay, just to simplify the notation, we are going to call this W up. Okay, it's an approximated solution. Okay, we can factorize by epsilon, so let's call this W up is theta W tilde 1 plus epsilon theta W tilde 2. And so W tilde I will be notation for, as we used here, okay, because it depends on 2 variables. Even if in reality, in our case, it only depends on z, but that's okay. W I tilde x over epsilon. And V up approximation in the fluid domain will be V0 plus epsilon V1 plus epsilon 2 V2. So which means that we have W epsilon x equal to W up epsilon W up x. Okay, so here we see that it's factorized by epsilon plus a remainder epsilon W epsilon R. And here we have V epsilon x equal epsilon, V up x plus epsilon V epsilon Rx. So, okay, we use here this. Just some remarks. Or, okay, maybe. So we are looking for a solution in this form. And the objective is to show that we are going to show that these remainders are bounded independently of epsilon. So let's assume that, so let's explain why this will be sufficient. So if we show that W epsilon R, which is in L2, this is the obstacle domain -1, 0, okay, in H1, if we are able to show that these remainders are bounded independently of epsilon, for W epsilon R also for V epsilon R, so V epsilon is the fluid domain 0, 1. If we show that this is will be the objective of the next part, then, okay, then what does it mean? It means that if I take the difference, let's say for V epsilon, then V epsilon minus V up H1, 0, 1 will be bounded by C epsilon, right? That's why, so we take this epsilon here. And W epsilon minus W up H1 -1, 0 will be bounded also by C epsilon. And what does this mean? What does this mean? So V up, you go back here. So it's V0 plus epsilon V1 plus epsilon 2 V2. And so this will imply that V epsilon minus V0, I can remove the other orders on epsilon because here I have something controlled by epsilon, which means we can use some inequalities here. And we can obtain that this is bounded by C epsilon. Okay? And what does this mean? So this is the convergence. This is we are answering here. If we are able to show this, this is answering our first question about the convergence. So this answers maybe a question that is posed here. Yeah, so how does the penalized equation is equivalent to the original problem? This is what we are going to show here. So it's not equivalent. What we show is that when epsilon goes to 0, the solution of the V epsilon, which is the solution of the penalized problem, will converge to the solution of the initial problem. So we replace the problem on the initial problem, we replace it by the penalized problem, and we are going to show that the solution of the penalized problem in the fluid domain will converge to the solution of the initial problem. So in practice, so instead of solving the initial problem, we are going to solve the penalized problem. And we are, if we have this result, the theoretical result, we are sure that if we take epsilon small enough, the error will be of order epsilon. Okay, and we can be satisfied by this in some time. So this is the link between the original problem and penalized problem. So this is convergence of the penalized solution towards the initial solution of our initial problem inside the fluid domain. Okay, so this is in the fluid domain, and this is if we are able to show this independence with respect to epsilon of the remainders. And here, well, this will give us that if we replace W up by the expression, so it's W epsilon there is some epsilon theta W W1 tilde. So we have the solution. Okay, so W1 tilde was this. So it's V0 prime exponential Z, and I take it as x over epsilon minus epsilon theta epsilon squared here theta W2 tilde 2, which was V1 0 prime exponential x over epsilon H1. Okay, well, this means that there is a boundary layer at the interface 0, and so theta is localized. Okay, so theta is localized on this part. So if we are far from the interface, we can just write W epsilon smaller than C epsilon. So we will also have a convergence to 0 of order 1 if we are far from the interface, but otherwise here there is some boundary layer terms that will occur. Anyway, so in reality what we are interested in is especially what happens in the fluid domain, but to be able to obtain this result, we need to consider all the problem in all the domain, because there are some connections, and so we need to also study what happens in obstacle domain. Okay, so what we are going to do is write the equations on these remainders. It's the same approach we used before. I am going to erase this. If I need something, I will recall it. We can erase this. And I will try to speed up because time doesn't wait for me. So maybe I will focus on the approach and maybe skip the details of the calculations. So, but the approach is the same. I will explain the procedure. We are going to write the equations on the remainders, okay? And to do that, well, we have the equation on W epsilon. And so we will write the equation on W epsilon, which was this. In omega, small omega. And then you replace, so if we look at a solution in this form, we can replace W epsilon by this expression, okay? So you replace by the expression, and then you try to separate the equation on W epsilon R, etc. So what we obtain is, I will just give the result, minus W epsilon R double prime plus 1 over epsilon square. This is the equation on the remainder, and it will be equal to something that that depends on W up, okay? And this we are going to call it right-hand side R epsilon obst, which means because it's it's the equation on the obstacle domain. The obstacle domain. Then we do the same thing. So if we write the equation on V, that was this. This was in omega. This is in the initial domain. The same, you can get an equation on V epsilon R. And you get an equation which is this one. And I call this R epsilon fluid. This is the equation in U. This is omega U. And then also you write the transmission conditions. So you write that V epsilon, you know that V epsilon at 0 is W epsilon 0. And this will give you a transmission condition also on the remainders. You obtain simply in this case that you have continuity at 0. Then you write that we have continuity of the derivative at 0. And this will give you, on the remainders, it will not be exact because, as we said, at the limit, it's not C1. So you will have some error here. And we will get that the difference between the derivatives on the remainders will be some in reality, if you calculate, if you write it, you will have minus epsilon v2 prime 0, and we call this R epsilon boundary. Okay, so you have this first transmission condition, this second one. And here you can understand why what? Anyway, oops, what is the epsilon boundary? So we have the objective is to write the equations on the remainders. We write it as a transmission problem. So what happens in the obstacle domain, the fluid domain, and then this transmission condition, and then on the boundary -1 and 1, it's simply because we localized the boundary layer terms, we get simply that V epsilon R -1 is 0 and W epsilon R -1 is 0. Okay, so here there is no problem. Okay, I have to maybe give just the ideas. Okay, so I have everything. I didn't explicit this epsilon obst. So for R epsilon fluid, we find that it's 0. Okay, you calculate, you replace V up, you will find 0. For R epsilon obstacle, this is, you have to calculate these derivatives. Okay, and W up is this, so you will have to calculate some derivatives. So replacing by this calculation, and so when you do the calculation, we end up with R epsilon obst. So this is something we already did for the reaction diffusion case, etc., the simplest case we saw. So it's simply calculating what gives this. And then you will see that some terms will simplify thanks to the equation satisfied by the correctors. But then we will have some remaining terms. So in this case, what you obtain is theta double prime W tilde 1 plus epsilon theta double prime W tilde 2. I don't write the arguments here, but when I'm talking about W tilde, it's x over epsilon. So we end up with these terms. The others will cancel using the equation satisfied by the correctors. And what we need is only estimates, okay, on this. So if you remember what we already did, so here we will need the expression of W tilde. You remember it was some exponential of z over epsilon, of x over epsilon, of z, when we replace it by x over epsilon. And we have just to notice that, and we can have here some power of epsilon that can be positive or negative. This will not pose problem. Anyway, so we will have some W tilde 1, for instance, is some constant exponential x over epsilon. When we derive it, you find the, when you derive with respect to z, we find the same function, okay? Because this is xz. So W tilde is also the same thing. And then what we take is the value at x over epsilon. So we will end up with terms of the form theta prime or theta double prime of some exponential of x over epsilon, which can be divided with some power of epsilon here, which can be negative, okay? But again, as we saw in yesterday and before, theta is equal to 1 near here, okay? So this is, so I mean, here the problem that we can get, because we want to have epsilon ops, we want it to be bounded independently of epsilon. Here we can get some problem if we have 1 over epsilon at the boundary. At the boundary, the value is 1 until we have some 1 over epsilon. But hopefully here all the terms are multiplied by theta prime or theta double prime. Normally there were also some terms with theta, but they simplified using the equation on the correctors. So we end up only with these terms, and this, because it's multiplied by theta prime or theta double prime, which is 0 near the boundary, which means that this is in reality, this f epsilon ops is 0 near the boundary. So we can just look at what happens at far from 0. Far from 0, if we are minus delta here, we can, as we already did, this will be smaller than exponential minus delta over epsilon. And this is an exponentially small term. It's smaller than any power of epsilon. So even if we have 1 over epsilon, we know that these terms will be some, it's smaller than any power of epsilon, actually. M. Okay. Okay, so it's exponentially small term. I will only need the boundness here, so let's just write that. So what we obtain when we do this, we can estimate the error in the epsilon norm. This is bounded independently of epsilon. And now what we are going to do is to what we want to estimate is the remainders, okay? And what we have the estimate of this. Also, this is something of order epsilon. This we will find that it's 0. So now we want to obtain estimates on the remainders, and what we do is the same approach as before. We are going to multiply the equations by this equation by this remainder and integrate by part. So the difference here will be that we will have some boundary terms, okay, because we don't have directly at 0, W epsilon R is not 0, and V epsilon R is not 0. So we need to do multiply this by the solution and integrate by part, this one as well, and then sum the two equations. Okay, so this is the last part, estimate of the remainders. Okay, so multiply this. This is equation, let's say 1, this is 2. So we multiply by W epsilon and integrate by part, and I will give just the last thing we obtain. Okay, so we will have some boundary terms as well. So the first equation will give, okay, so this we multiply by W epsilon R and integrate, and we will get W epsilon R L2 prime L2 square. Okay, I don't precise here, so maybe precise. So this is the obstacle domain. It's -1, 0 plus 1 over epsilon 2 W epsilon R L2 square will be equal to the integral from -1 to 0 of R epsilon obst W epsilon R, and we will have some boundary terms, okay, that will not be 0 here because we don't know what these will be equal to. And then equation 2, you do the same thing. We multiply by V epsilon, integrate by part, and you end up with V epsilon R prime L2 on 0, 1 this time, plus equal some boundary term. Okay, and then we sum the two equations. So we sum the two equations, and you end up with W epsilon R prime L2 square plus 1 over epsilon square W epsilon R L2 square plus P epsilon R prime L2 square. So each time it's L2 on the corresponding domain, fluid or obstacle. And on the right-hand side, you will have the obstacle -1, 0 W epsilon R plus these two terms. We can, and we know that there is some. We know that we have continuity for the remainders at 0. There is a jump only on the derivative, so we can factorize with the W epsilon R 0, for instance, and this will be multiplied by W epsilon R prime 0 minus V epsilon R prime 0, and this is what we called, or maybe in the other, there was a minus. So yeah, there was a minus here. Okay, so this is minus our epsilon boundary. Okay. Okay, so we are almost done, because now the objective is just to, so we have this this equation, and we are going just to use Cauchy-Schwarz inequality, Young inequality, things like that, in order to deduce an estimate on this W, epsilon R, etc. Okay, so the right-hand side, okay, let me write what we have on the left-hand side maybe first. This was this plus 1 over epsilon square W epsilon R plus P epsilon R prime L2 squared smaller than so we use Cauchy-Schwarz, so this is R epsilon obst W epsilon R L2 W epsilon R L2. And then for this term, we are going to use the continuity. So W epsilon R is in H1 minus 1, 0. So we can, and R epsilon boundary, it's a constant of order epsilon. So this will be smaller than epsilon times some constant by continuity of the trace, the norm of W epsilon R L2. And then we are going just to use some Young inequality. So let me write the form in general here. So AB, if you write AB like A over alpha, alpha B, then you can use just the fact that this is smaller than 1 over 1/2 A squared alpha squared plus alpha squared B squared over 2. So you can choose in reality this to be 1, for instance, and this is what we are going to use here. So this is smaller than if W epsilon R L2 squared plus some constant, this R epsilon obst L2 squared plus where is the sorry, here I used the fact that it's H1, right? We used the continuity of trace, so it's H1. So here W epsilon R is not in H1 0, but we have on one part W epsilon R at -1 is 0, and in this case we also have a Poincare inequality that holds. Okay, if we have only 0 on some boundary, so we can use here that it's we can take some constant, the norm of the derivative. Yeah, and so this is by Poincare inequality. We are not in H1 0, but Poincare inequality holds if we have 0 at some endpoint, which is the case here. This is smaller than some constant, the norm of the derivative. Okay, so because here I want to absorb this with this, for instance, this norm here, we need to take a good constant, which can be 1.5. for instance. So we are going to take 1/2 for L2 squared, and then here we are going to have C, just by using the Young inequality, this will be C epsilon squared for some constant C. And now, so we are going to absorb everything on the left side. So here we have 1 minus 1/2 is 1/2. For this one, we have 1 over epsilon squared minus 1. And then we have the V epsilon R prime is 2 squared. And on the right-hand side, we saw that this is bounded. In reality, this is exponentially small, but it's okay. We have something C plus C epsilon squared. And for when epsilon goes to 0, this is the positive. So for epsilon small enough, this will be positive, and we end up with these estimate. This is smaller than, so this will be smaller than epsilon, C epsilon. For W epsilon R, L2 also will be smaller than, just I need only the boundness for the moment. As we said here, we only need to bound it to obtain the convergence. So let's stick to that. This is smaller than C. This is as well, and V epsilon R prime L2 is smaller than, bounded independent of epsilon. And this gives the H1 norm. And here again, we can use Poincare inequality because V epsilon R at 0.1 is 0. So Poincare inequality holds, and this allows to obtain V epsilon R H1 norm also bounded by independently of epsilon. So with this, we are done. Sorry for the timing. So we finished here because we were able to bound the remainders independently of epsilon here. And so what we wrote already here follows, and so the convergence of the penalized solution towards the solution in the initial problem. Okay, so I wanted today to treat also Newman boundary conditions, but I think that was too optimistic if I explain all the calculations. But so this is it for this example for Dirichlet boundary conditions. I suggest to stop here, and tomorrow we will continue with the Newman or Robin boundary conditions. And I will not detail everything. I will maybe have some notes that I will share with you and explain the differences, because we are going to see that there are some differences with the Dirichlet case. Okay, thank you very much for your attention, and see you tomorrow.